Confidence intervals for the mean when sigma is unknown. Before I begin, keep in mind that usually sigma is unknown, so this section is the more common situation. Confidence interval for mean when sigma is unknown, Part 1. The Arctic Sea ice extent measurement for a sample of 37 days showed a mean of 11.9 million square kilometers and a standard deviation of 0.4 million square kilometers. The sample mean of 11.9 million square kilometers is called a point estimator for the population mean. The problem with point estimators, like the sample mean, is that they can be unreliable due to sampling error. The population mean at a given point in time is a fixed value and would reside somewhere on the number line. When sample data is gathered and a mean is calculated, that sample mean can be slightly smaller than the actual population mean, or it might be larger than the actual population mean. It is impossible to know exactly where a sample mean lies in relation to the population mean unless the population mean is actually known. When the population mean is not known, we will increase the reliability of our estimate by constructing what is called a confidence interval estimate that will be centered at the sample mean and surrounded by a margin of error. We would begin by calculating the sample mean. We would then add the margin of error to the sample mean and then subtract the margin of error from the sample mean. So our interval would assume the form of x bar plus or minus e. The margin of error, when calculating a confidence interval about a single mean, is determined by three factors: the t-value, the sample standard deviation, and the sample size. The t-value is taken from a distribution known as the student t-distribution. This table shows an excerpt from a table of t-distribution values. Note the abbreviation in the left column df. This refers to the number of degrees of freedom. For this application, the number of degrees of freedom is one less than the sample size. Note the top row gives varying confidence levels. The highlighted example would be for the construction of a 95% confidence interval with 21 degrees of freedom. Let's construct a 95% confidence interval estimate for the population mean Arctic sea ice extent. Certain assumptions must be made when constructing a confidence interval estimate for the population mean when the population standard deviation is unknown. The first assumption is that the sample is a random sample. The second assumption is that either the sample size is greater than or equal to 30, or the population is normally distributed when n is less than 30. So we will calculate the margin of error, then add it and subtract it from the sample mean. Recall that the calculation of the margin of error requires the use of the values from the t-distribution. Our confidence level is to be 95%. The number of degrees of freedom will be one less than the sample size, so 37 minus 1 is 36. So we will examine in the table and look across the top row for our 95% confidence level. So this is the column that we will get to our t-value from. Now we'll drop down until we find 36 degrees of freedom and find out where that crosses up with the 95% column. And we have a value of 2.028. So we will calculate the left and right hand endpoints of our confidence interval by substituting the sample mean, t-value, sample standard deviation, and sample size. The resulting interval endpoints are 11.8 and 12.0. Our interpretation of this interval will be stated as follows. It can be stated with 95% confidence that the population mean Arctic sea ice extent is between 11.8 and 12.0 million square kilometers. Confidence interval for mean when sigma is unknown, part 2. The Antarctic sea ice extent was measured for a sample of 37 days also. The mean was 9.9 million square kilometers, and the standard deviation was 4.7 million square kilometers. So let's calculate the margin of error, then add it and subtract it from the sample mean. Recall that the calculation of the margin of error requires the use of a value from the t-distribution. Our confidence level is to be 95%. The number of degrees of freedom will be 1 less the sample size, so 37 minus 1, or 36. So let's examine the table and look across the top row for the 95% confidence level. So this is the column that we will use to get our t-value from. Now let's drop down until we find the number 36. Let's find out where those cross up. With the 95% column, we have a value of 2.028. Again, calculate the left and right hand endpoints by substituting the sample mean, t-value, sample standard deviation, and sample size. The resulting interval endpoints are 8.3 and 11.5. Our interpretation of this interval will be stated as follows. It can be stated with 95% confidence that the population mean Antarctic sea ice extent is between 8.3 and 11.5 million square kilometers. The interval for the Arctic ice sea extent was a bit narrower than that of the Antarctic sea ice extent. Note that the standard deviation for Antarctica is considerably larger. This caused a margin of error to be greater, which resulted in a wider interval. Let's go ahead and follow along with your student notes. As mentioned earlier, most of the time, sigma is unknown. So it is estimated by the sample standard deviation S. When S is used, especially when the sample size is small, critical values greater than the values for z subscript of alpha over 2 are used in confidence intervals in order to keep the interval at any given level. These values are taken from the student t-distribution, most often called the t-distribution. The t-distribution. The following are the assumptions required to use the t-distribution. First, the samples must be simple random samples. Second, the population from which the samples are selected must be normally or approximately normally distributed, or the sample size must be 30 or more. Here are some properties of the t-distribution. The t-distribution is bell-shaped. The t-distribution is symmetrical about the mean. The mean, median, and mode are equal to 0 and are located at the center of the t-distribution. The curve approaches but never touches the x-axis. The standard deviation is greater than 1. The t-distribution is a family of curves based on degrees of freedom, which is related to the sample size. As the sample size increases, the t-distribution approaches the standard normal distribution. As we can see in the next slide, once again, as the sample size increases, the t-distribution approaches the standard normal distribution, as you can see here. Notice that when I go from the degrees of freedom of 5 to the degrees of 3 to the degrees of freedom of 20, we get closer to the standard normal curve. The degrees of freedom are the number of values that are free to vary after a sample statistic has been computed. The degrees of freedom, df, for a confidence interval for the mean is found by subtracting 1 from the sample size. Thus, the formula for degrees of freedom will equal to n minus 1. Now let's take a look at the critical values for the t-distribution, that is to say, t with the subscript of alpha over 2. Critical values for the t-distribution at specific confidence intervals and degrees of freedom are found in Table F or by using your graphing calculator. Let's go ahead and look at an example. Let's find the critical value, t subscript of alpha over 2 value, for a 95% confidence interval for a sample size of 25. First thing we do is look for the degrees of freedom, which once again is 1 minus the sample size. In this case, my degrees of freedom is 24. So we first start off by looking for the number 24 in the left column labeled df, in the table that you saw on the previous slide. Now find 95% in the row labeled confidence intervals. Here, the critical value will be 2.064. As a reminder, once again, we first look for 24 in the df column. And then we also look for the column of 95%. We take a look at where they intersect. And as you can see, they intersect here at 2.064. Once you find the critical value, you will then be asked to plug it into this compound inequality. The idea behind this compound inequality is to ensure that our mean is somewhere in this interval, by whatever confidence interval you establish. Again, keep in mind the degrees of freedom are n minus 1. Let's take a look at an example. The number of students who belong to the dance company at each of several randomly selected small universities is shown here. Estimate the true population mean size of a university dance company with 99% confidence. The data are listed below. First, find the sample mean and standard deviation for the given sample. You should recall how to find sample mean and standard deviation from previous lessons. Here we get our sample mean as 29.8 and our standard deviation as 6.176. I invite you to pause the video and confirm that these two values are accurate. It is important that you pause the video here and try this yourself to remind yourself how to find the mean and the standard deviation, once again, using the concepts from previous sections earlier this semester. Second, find the degrees of freedom. Here, it'll be 19 minus 1, since there are 19 data points. That gives us degrees of freedom of 18. Now we'll use the table to find the critical value. Pause the video here and confirm that 2.878 is our critical value for when you have degrees of freedom of 18 and you're looking for a confidence interval of 99%. Now go ahead and calculate this expression here. Essentially, take the critical value that you just found and multiply it times the standard deviation divided by the square root, in this case, of 19. Recall here that n is equal to the sample size itself. Once the sample size is calculated, Go ahead and enter it into your compound inequality. We will add and subtract from the sample mean. Again, here's the formula. We know our sample mean, and we just calculated this expression here, which is 4.08. We will simply subtract and add to the 29.8, giving us 25.72 is less than the mean, which is less than 33.88. This means that we have 99% confidence that the mean is between 25.72 and 33.88. Next, for a random sample of 24 operating rooms taken in a hospital study, the mean noise level was 41.6 decibels, and the standard deviation was 7.5. Find the 95% confidence interval of the true mean of the noise levels in the operating rooms. Since we already have the mean and the standard deviation, we can just jump right in. Our degrees of freedom here will be 23, since that's one less than the number of operating rooms. Now, pause the video here and confirm that the critical value that we get in this particular case is 2.069. Now, once again, we go ahead and calculate the expression of the critical value times the standard deviation divided by the square root of the sample size. In this case, I get 3.17. Now we take this 3.17 and we're going to add and subtract it from the sample mean. Again, here's the formula. 41.6 minus 3.17 and 41.6 plus 3.17. And so we have a confidence level of 95% that our mean will be between 38.43 and 44.77.